We're going to discuss one way to arrive at the expression for the energy density in a magnetic field, if you prefer the magnetic energy density. And just so we know where we're headed, I'm going to say at the beginning that we would write UM, the energy density, is a half H dotted with B. And of course, in a vacuum, we can change that to UM is equal to a half 1 over mu naught B squared. That's just so that we know where we're headed with this derivation. So what we're going to do is we're going to consider an argument about circuits. So if we have a closed circuit of some kind, which is carrying a current I, and there is a magnetic field associated with it which is cutting through the circuit, then in general there'll be an EMF which is induced by the magnetic field, and so we can write the standard equation that V plus the EMF is equal to IR. That's a circuit with resistance R. In other words, and then if we think about the work that must be done to move a small piece of charge dq around the circuit, we can say that we would have V dq is equal to V I dt, if we're assuming that small charges are just the current for a small part of time, which is minus EI dt plus I squared R dt. Now I squared R dt, this is just ohmic losses, so that's essentially turning the work into heat, so we're not interested in that because that's not storing energy in the fields. So we're going to say that the small amount of work done in this system is going to be I EMF dt, which of course is also written as I d phi, where phi, remember, is the flux of the field through the circuit, because the EMF is minus d phi by dt. And now we're going to build that up. We're going to assume that if we're thinking about a magnetic material, then we could construct a careful argument where essentially we broke the material down into small closed loops and then we just integrate it over the volume of the material. So for now, we're going to just think about a set of circuits which we're going to sum over. So therefore, so if we now have a set of circuits, which will allow us to build up to that, then in this case, the work done in moving charge around those circuits is going to be a sum over the circuits. Let's say we've got n circuits, and it's going to be the current flowing in each circuit multiplied by the flux cutting through each circuit. Now, so long as the circuits themselves are rigid and we're in linear materials, we can start at zero current and then just gradually increase over time, and we're going to do that by writing the current at any given time as an I prime, which is going to be some parameter alpha multiplying the final current, and alpha is going to go from 0 up to 1, and that will allow us to integrate over time. Of course, if we're doing that, then we also have to think about increasing the flux over time. So we have d phi I is a d alpha multiplied by phi I, and so then we're going to integrate over alpha, so the integral of dw, which is just w, is the integral from 0 to 1 d alpha, the sum from I is equal to 1 to n of I alpha phi I, which of course is just a half times the sum over all of these different circuits of I multiplied by phi. And at this stage, it just pays to take a brief moment to look back up here and see that we've got V dq, so that's the electric potential multiplied by a charge. And remember, charge, of course, is the source of electrical fields and electrical potential. Over here, we have a current, which is the source of magnetic fields, multiplied by E dt. Now, E dt we've just said is d phi, so that's the integral of a magnetic field. So we will see in a moment that actually the formula for the energy in a magnetic field can be related to the current density dotted with the vector potential. So there's this lovely symmetry, as you would expect, that you have the source of the field, so either the charge or the current charge density or the current density multiplied by the potential, either either the scalar electric potential or the magnetic vector potential, giving us the energy. And we'll see that in a moment. So to see that, in fact, let's just recall that the flux cutting through a circuit, phi I, is going to be the closed, is going to be the surface integral of B dot n dA. So that's the magnetic field passing through the surface defined by the circuit, and that of course can be turned to a closed loop integral, Ci of A dotted with dLi, because we're using the fact that the curl of A is equal to B, and we can use Stokes' theorem to transform the surface integral of a curl to a loop integral. So now we find that we have W is equal to a half times the sum over the circuits of a loop integral of I A dotted with dLi. Now, we're actually interested in the magnetic energy density in a general system. So we're really not wanting to think about circuits, but we're wanting to think about current densities. And so it is possible to show that we can replace the sum and the loop integral with a volume integral, and we can replace I dLi, of course summed with a current density, and so the total energy in this system becomes the volume integral of J dotted with A dV. And that's, as I mentioned, a lovely symmetry. The total energy in an electric field would be the volume integral of rho V dV, where that's an uppercase V for the potential, a lowercase p V for the volume element. We can actually go further and convert this into an expression involving B and H. So first of all, we're going to say that we've got curl of H is equal to J, and so we find that J dotted with A is written as curl of H dotted with A. Now we're also going to just use the following expansion. The divergence of a cross product, div of A cross H, is H dotted with curl A minus A dotted with curl H. Oops. And so now we can substitute both of those in and say that W is equal to a half times the volume integral of H dotted with the curl of A minus the divergence of A crossed with H dV, the volume. But we know what the curl of A is, that's just the magnetic field. So that's equal to a half times the volume integral of H dotted with B dV minus the volume half the volume integral of the divergence of A crossed with H. And here we've used B is equal to curl A. And now here we're going to use the divergence theorem to change this volume integral into a surface integral. So W, the total energy, is half the volume integral H dotted with B dV minus half the closed surface integral of A cross H dotted with N dA. And we're now going to use an argument which is essentially the same as the argument we used for the energy density in an electric field, to argue that this second integral will tend to zero as the volume we integrate over is taken to large, it essentially tends to infinity. The argument essentially is this: we have a magnetic field defined in a small area around the origin, so that if we just confined our volume to the area where the magnetic field was non-zero, then of course the first term would give us the energy stored, and the second term would give us some kind of contribution Now, if we increase that volume, assuming that we've got vacuum everywhere else, the first term doesn't change because integrating over the volume of 0 just adds 0 to the integral. The second term, we are expanding our surface area to larger and larger sizes. The point is that A is going to go as 1 over r, it's going to change with 1 over r, h is going to be proportional to 1 over r squared, and dA is proportional to r squared. So the total integral scales as 1 over r, which goes to 0 as r goes to infinity. And therefore we can say that the energy density, U, is a half h dotted with b, and then W is just the volume integral of U dV. So this shows us a way to find the energy density in fields which involve magnetic fields and also magnetic media.